We're going to look at verifying trig identities. This will be similar to the problems that we looked at in the last part of this lesson on simplifying. So we're going to use some of the same strategies as we use there. We're going to factor sometimes, but remember we said that one's pretty rare, but it's something to look for. We're going to make substitutions from our identity list. We're going to change into sines and cosines. But when we say we're verifying a trig identity, the difference between these problems and the ones that we looked at in the last part that said simplify, where the verify questions will be an equation, whereas the simplify ones were just an expression. There was no equal sign in them. So when we're verifying, we can take advantage of the fact that it's an equation, and we can do equation stuff. So we can add, subtract, multiply, divide on both sides, and if it's a proportion, we can solve by cross multiplying. So we have a couple extra things that we can do with verifying. With simplifying, I said that one of the problems students have with simplifying is never knowing when you've done enough. Like, how do I know that this is simplified enough to be called done? With verifying, that's not an issue, because in verifying, the goal is to make the two sides of the equation exactly the same. So like 1 equals 1, cosine equals cosine. Okay, so the two sides match exactly, or making it exactly match one of our trig identities that's on the top of your worksheet. Because those are identities. They are things that are definitely true. And the goal of verifying is to show that this is true. So in verifying, it is the work that matters. Everybody's final answer could look slightly different depending on the methods that you choose to use to verify it. But the goal in verifying is that whatever you end up with, you should have something equals itself. And so it's the work of getting there is what matters. So on your homework, no work, no credit. On the test, no work, no credit. Because it doesn't so much matter exactly where you end, it matters how you got there. So one of the most popular strategies, one of the strategies that we will use a lot, is looking for substitutions. So when I see a negative angle in there, I'm going to check the negative angle identities in the substitution list. Is cotangent of negative theta on the negative angle identity list? No, sine, cosine, and tangent are, but cotangent is not. So then another popular strategy is to rewrite what I would call the three minor trig functions, the cosecant, secant, and cotangent, in terms of the others. So how could I rewrite a cotangent? What is cotangent equal to? It's the reciprocal of tangent. So I could rewrite this as 1 over tangent. Angles stay what they are. So of negative theta, and on the other side, that negative hang out up front, and 1 over the tangent of theta. You could also turn tangent into cosine over sine, because that's true as well. So that would be a different option of something to do that will still result in a correct end. Now we'll check that identity list again. Is tangent of negative theta on the identity list? What does the identity list say that that is equal to? The negative tangent of theta. So we're going to make that substitution from the list that tangent of negative theta is equal to a negative tangent of theta. On the other side of the equation, I'm just going to carry it down. I'm not doing anything over there. The goal of verifying is to show that what we started with is true by simplifying it down until we can see that it is definitely true, that something equals itself. And we have that at this point. Both sides have a 1 over a tangent of theta, and both sides have a negative, so this problem is done. Both sides of the equation are exactly the same. Both sides have a 1 over a tangent of theta and a negative out front. Remember, in a fraction, it doesn't really matter where the negative is, top, middle, or bottom. It's just that it's negative. This one has that negative angle again, but we said last time the identity list only gives us the 3 big ones, not the 3 minor ones. So how can I rewrite a secant?
1 over cosine.
1 over cosine. Secant is the reciprocal of cosine. Then we check the identity list again. Is cosine of negative theta on the identity list? What is cosine of negative theta equal to? Just a plain cosine of theta. And when we make that substitution, the 2 sides of the equation are now exactly the same. They both have 1 over cosine.
How do we get rid of the negative?
By doing a substitution from the identity list. On the identity list, under the negative angle identities, it says the cosine of negative theta is equal to the cosine of theta. So we're doing a substitution out of the identity list. Yes. Theta and x, it doesn't matter what it is. So if on the identity list it says x or theta, and our problem it says the other one, it doesn't matter. X's and thetas all mean the same thing. It just means a variable. For the next one, there are many different things we could do first. Some of them will get us to our final destination faster than others. I'm never going to grade you on you did the fastest way, or the point is, did you get there eventually? Okay? So don't worry about if you're doing the most efficient way or not. That's something that could come with kind of time and finessing our skills on these. At this point, it's just, can we get there, even if we take some detours along the way? In fact, in showing this problem, I'm not going to take you the fastest way, because the fastest way is something that I notice after doing these things for a while. But the way I'm going to show you is a way that we could just kind of do the same thing every time, and we'll get there eventually, even though it might not always be the fastest way, just so we have a method and a routine to our strategies. That tends to make it easier for students to learn. First thing I'm going to choose to do is get rid of the fractions. I don't like fractions, so I'm going to get rid of the fractions. Since this is an equation, we can take advantage of the fact that it's an equation and add, subtract, multiply, divide, as long as we do it to both sides. So I'm going to multiply both sides of this equation by the cosecant of x. We cannot do that in problems that just say simplify, because they don't have an equal sign. So then if we start multiplying by something, we're changing what it is. And we can't do that. You can multiply by 1, but you can't multiply by anything else because that changes what. But in an equation, we have that added benefit of being able to multiply an equation by whatever we want, as long as we do it to both sides. So on the left-hand side, those cosecants cancel, leaving just a cotangent squared of x. On the right-hand side, we're going to distribute. A cosecant times a cosecant would make a cosecant squared. And then sine times cosecant.
Why isn't the x in the first cosecant, like on the right side, why isn't that x squared?
When we multiply cosecant by itself, or any trig function by itself, we're multiplying the function by itself. We're not multiplying the x by itself. So it is the function that becomes squared, not the x that becomes squared. You could also write it as the whole thing squared, but you cannot just write that the x is squared. So we're multiplying the function by itself, not the x by itself. All right, so next, I'm going to choose to turn this thing into sines and cosines. That's one of my favorite strategies. I do that a lot in these problems. So cotangent is what? It is 1 over tangent, but let's put everything in terms of sines and cosines. Cosine over sine. Since cotangent was squared, both of its parts will be squared. So cosine squared over sine squared. What is cosecant the reciprocal of? Sine. So cosecant squared becomes 1 over sine squared. Sine is just sine. I like to put it over 1 just so that everything's a fraction, but you don't really have to do that. Just like everything to be consistent. And cosecant, we said, was the reciprocal of sine. The goal of changing everything into sines and cosines is that ideally when we do that, something will cancel. We can cancel when we have multiplications. So in the part of this problem where there's a multiplication, does anything cancel? Yeah, there's a sign on the top with a sign. So those are gone. So now I've got cosine squared over sine squared equals 1 over sine squared. And it doesn't cancel to disappear. It cancels to make 1. That's like multiplying 2 over 1 by 1 over 2. It becomes 1. It doesn't become 0.
Can you explain this like from the green to the blue? Because I'm lost.
Yep, from the green step to the blue step is where we did the strategy of changing everything into sines and cosines. So we talked about that strategy in the last part of the lesson, where we said a long time ago in trig, we learned that tangent was equal to sine over cosine back when we studied our unit circle. So we can take a tangent and replace it with a sine over cosine. Or likewise, a cotangent would be a cosine over a sine. And then our two reciprocal functions, cosecant is the reciprocal of sine, and secant is the reciprocal of cosine. So we're making those substitutions based on what we did back with the unit circle. So cotangent became cosine over sine, and cosecant became 1 over sine. All right. I, in my very first step, chose to multiply to get rid of fractions, and then now I'm doing that again. So I'm going to multiply again to get rid of fractions. They just keep on showing up. What will I multiply by to get rid of fractions? Sine squared x. We'll get rid of all the fractions in this equation, and we need to multiply the whole equation, every part, by that sine squared x. Yep. We're not done yet because we still don't have a clear something equals itself or a definite true identity. So I get cosine squared of x equals 1 minus sine squared of x. This is our step. One more step and we're done with this one. So I said there's two ways we can say a problem is finished. We can say it is finished if something exactly equals itself. 1 equals 1, 4 equals 4, cosine equals cosine. Or we can say we are finished if we reach an identity that we already know to be true. So those identities that are on the front of your worksheet are things we know to be true. So if we can make it match one of those, we can say that we're done as well. This looks a whole lot like the first identity. What does that first identity say? Sine squared of theta plus cosine squared of theta equals 1. Remember, thetas and x's don't matter. So if we can make this look like that, then we can be done. What do we need to do to make it look like that? Add the sine squared x over to the other side. And that now matches something on our identity list, so this problem is completed.
How did people find these answers?
How did they find the original identities? There's three types there. The Pythagorean identities come from the idea of the right triangle and the unit circle. And remember that we said if it's a unit circle, our radius is 1. And we said that any point on the unit circle was cosine, comma sine. So that means that y would be sine and x would be cosine. And if we do the Pythagorean theorem on that, we would get sine squared plus cosine squared equals 1, which is that first Pythagorean identity. And all the other Pythagorean identities come from this one. As far as the other two groups there, the cofunction and the negative angle identities, those are most easily seen by looking at the graphs, actually, and thinking about shifting. Like when we shifted our graphs to the right or to the left, that's where those other cofunction identities come from. So they all come from things that we've already done. We just didn't take the time to prove the identities themselves. We're just going to accept them.
Wait, so if you... Oh, okay. Right.
If we do a squared plus b squared equals c squared on that picture, it gives us sine squared plus cosine squared equals 1 squared,
Okay.
which is that first identity.
How did someone come up with like the original like sine, cosine, and tangent? Aren't those like ratios or something?
Yeah, sine, cosine, and tangent are ratios of angles. Why they decided to call them sine, cosine, and tangent, I have no idea. But they just said, let's start taking ratios of triangles, and we have to give it a name, so they give it those names. I don't know why.
Well, why? Like, how do they? Like, what ratio are they? Like you said.
Sine is opposite over hypotenuse, cosine adjacent.
Okay.
It's just those SOHCAHTOA ratios. All right.
Okay, I'm really not trying to be mean here. No, I'm saying this, like, I don't understand this at all. Like,
Then stick with me. We're going to do more examples, and if we need extra help, I'm around.
I just don't get the point.
We talked about on Friday, the point of this is to build logic and build rule following, actually. So that's what we're building here, logic and rule following. So let's continue with that. In this next one, again, there are many things I could do first. I'm going to choose to, on the bottom of this, say whenever I see ones, that reminds me of those Pythagorean identities. So look at your Pythagorean identities and see if that is on the list somewhere. It is equal to secant squared. So what we are going to do is change the bottom of this fraction into a secant squared according to a substitution from that identity list. What can we do then?
We can just divide.
Then we can simplify and reduce. Because this is a multiplication, and this is very important, this is one of the biggest algebra mistakes that students make, you can only cancel and reduce in a fraction if there's no addition and multiplication. If there's addition or multiplication, you cannot cancel in a fraction. But because this fraction has no addition or subtraction, we can cancel out one of those secants. So that leaves us now with a cosine over a secant. I don't like fractions. So whenever I have fractions, one of the things I like to do is try to get rid of them. How would I get rid of this as being a fraction?
Timesing everything by the secant of x.
Multiply everything by the secant of x. So that gives me a cosine of x is equal to a cosine squared times a secant. The two sides still do not exactly match, so we are not done. What's another strategy I really like? Sine and cosines. So cosine can be cosine. Can put it over 1 if we want. Cosine squared can be cosine squared. We can put it over 1 if we want. What will secant become? 1 over cosine. Secant is the reciprocal of cosine. The goal of changing into sines and cosines is that ideally something will cancel. Anything cancel here?
Yeah.
One of those cosines goes away. So I am left with now cosine of x is equal to a cosine of x, which is definitely true.
So, one thing I just have trouble with is knowing when to stop when I'm done.
You're done when the two sides are exactly the same,
Or if we get
or
one.
if you get one of those Pythagorean identities. Until that point, keep on working.
Or if we get one answer.
When we're simplifying, so when we're doing the problems like we did in the last part, it is harder to tell when you're finished. On the simplifying ones, if you can get it down to just one term, you're definitely done. If you have more than one term, run through your checklist one more time, and if nothing happens, then you're done.
So you said if you can also get it equal to one of these Pythagorean identities,
Yes.
you get it equal to a cosine.
Yeah, as long as it equals any of the identities, it'll be done. Typically, though, it's going to be one of the Pythagoreans.
Oh, okay.
But any of the identities would be okay. All right, on this one, I got lots of fractions. I'm going to get rid of them.
Do you need to memorize all those?
You do not need to memorize any of the identities. They will all be given to you on the test. You do need to memorize how to change into sines and cosines, though. So like tangent is sine over cosine, that's something you should know. But the ones that are printed on the sheet will be on the test for you. This is a fraction equals a fraction, otherwise known as a proportion. How do we solve those? Cross multiply. So we're going to cross multiply this, which gives us sine times sine, which is sine squared. And then the other ones, we're going to need to multiply 1 minus cosine times 1 plus cosine. How do we multiply when we have groups of two things like that? We FOIL or distribute through. So that gives me 1 plus cosine minus cosine minus cosine times cosine, which is cosine squared. So when we have groups of two things, we FOIL or distribute. One of the other reasons why we do trig identities is because they cement our earlier skills. So foiling something we learned a while ago, and we kind of cement that skill as we reuse it. What do you notice happens here? In the middle, we've got a plus cosine minus cosine. Anytime you have something minus itself, that becomes 0, so that stuff's gone. So now I've got sine squared of x equals 1 minus a cosine squared of x. Squared stuff in ones reminds me of those Pythagorean identities of sine squared plus cosine squared equals 1, but I need to make it look exactly like that, so what do I do? Add that cosine squared over to the other side. And that's done. One more example, as is often the case in math. As we go through examples, the problems become more intense. I'm just going to throw this out. This is our longest example. It's the last one is the longest one, just so you know. Write accordingly. We begin with a fraction equals a fraction, which is a proportion. What do I do to clean out a proportion? Cross multiply, like we did in the last problem. So I'm going to do a secant times a cosine squared of x. Then for that other diagonal, I'm going to need to do the 1 plus sine times the secant minus tangent. And we're going to need a FOIL like we did on the last one. I'm just going to go ahead and write out the FOIL here instead of writing the two parentheses and then FOILing to save myself a line of work, since, like I said, this one will take the most.
Could we change the secants to cosine over 1 first to make it a compound fraction?
You could change the secants into 1 over cosines and make compound fractions. It's probably not the easiest way. It makes things more messy. It gives us more fractions instead of less fractions, but it's legal. It just might not be as obvious what to do from there. So I'm going to distribute the 1. That gives me secant of x minus tangent of x. And distribute the sine, which gives me plus sine x, secant x, and minus a sine x, tangent of x. So this problem looked a lot like the last one in the start, a fraction equals a fraction, but in the last one, something kind of pretty happened for us when we did that distributing, that some stuff dropped out. And on this one, it's just not looking like that's happening for us. So where might we go from here? What's one of my favorite strategies? Change everything into sines and cosines. So secant becomes a 1 over cosine. Cosine stays cosine. If it's squared, it stays squared. Secant becomes 1 over cosine. Tangent becomes sine over cosine. Sine stays sine. I like to put it over 1. Secant becomes 1 over cosine. Sine goes over 1. Tangent becomes sine over cosine. So just turn everything all the way through into fractions so that everything is sines and cosines. And the goal of doing that is that something will cancel. We can cancel anytime we have a multiplication. So we'll look at each time we have a multiplication in here. So on the left, there's a multiplication. Does anything cancel? Yeah, one of those cosines cancel out. So over there, I have now just a cosine of x. The first fraction is not multiplied, so there's no way to cancel anything there. The second fraction is not multiplied, so there's no way to cancel anything there. Then I have a multiplication. Sine over 1 times 1 over cosine. Does anything cancel? No. When we multiply fractions, common student mistake, we do not cross multiply. We cross multiply when there's an equals between them. This is a times between them. So we just smoosh them together, multiplying straight across. Sine times 1 over 1 times cosine. And in that final multiplication, does anything cancel? No, unfortunately the two are in the same place. They're both on the top. So we'll smush these two fractions together. So I get sine squared of x over cosine of x. Now that feels disappointing, but something nice did happen. Does anybody notice something nice that showed up here? In the middle, we've got a minus sine over cosine and a plus sine over cosine, and all the denominators are the same, which is a really nice thing too. So we have a lot of stuff matching now. In the middle, we have a minus sine over cosine and a plus sine over cosine, so those wash each other out. And all of our denominators are the same, which is going to come into play for our next step. Since all of the denominators are the same, what can I do to get rid of them? Multiply by it. So I'm going to multiply this whole thing by a cosine of x, which would give me a cosine squared of x, 1, and a sine squared of x. Whew, that feels good. What do you notice? It's basically the Pythagorean identity. Add that sine squared to both sides, and we're done. Keep those strategies in mind. A lot of students will say to me, like, okay, when you were doing it, I could kind of track along, but when I have a blank paper in front of me, I have no clue where to start. Good places to start: check for substitutions, change into sines and cosines. If it's an equation, multiply both sides by something. If it's an expression that says simplify, you can't do that. But if it's an equation, you could multiply both sides if you have fractions going on in there. But you can always look for substitutions. You can always change into sines and cosines. Those are good places to start. Okay? Your homework, you will notice, is all odds. That means you may check your answers, but no work, no credit. Okay? These problems require work. So if I don't see that work, you don't get